Hi, thanks for joining me today. I've got an interesting problem from the Imperial College Maths competition, and you can probably guess what year it comes from the problem. A tan vector is a non-zero vector in R cubed with integer entries. Prove that any tan vector of length at most 2021 is perpendicular to a tan vector of length at most 100. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to dive straight into a solution. Okay, so the way we're going to prove this result is by contradiction. So what we're going to do is first introduce some notation. I'm going to let Sn be the set of tan vectors with length at most 100. Not 100, with length at most n, sorry. So they're at distance at most n from the origin, where we look at the kind of Pythagorean distance, the Euclidean distance, L2 if you wish. Anyway, Sn is this guy here. Now, what are we going to do with it? Well, we're going to prove this by contradiction. So we're going to suppose for contradiction that there is a tan vector of length 2021, which is never perpendicular to any tan vector of length at most 100. So in other words, there exists some vector v, which is in S 2021, such that v dotted with any vector in S100 is never 0. So now what I'm going to do is take two arbitrary vectors u and w, where u does not equal w, and they're both from S50. And now, what do I know about u and w? Well, they are tan vectors, so neither of them are 0. And in fact, because they're different, when I look at u minus w, that's not going to be 0. But also u and w have integer entry, so will u minus w. And since u and w are distant at most 50 from the origin, that means u minus w, by the triangle inequality, must have distance at most 100 from the origin. So in fact, u minus w must be in S100. Now why is this interesting? Well, because of the property of the vector v, we know that v dotted with u minus w can never be 0. So in other words, v dotted with u can never be the same as v dotted with w. So what have we proved? We've proved that if we take any two vectors from S50 and dot them with v, we're going to get different numbers. And in fact, we can go one better, because we know that everything here is to do with integers. V, u, and w have to have integer entries. And so we know that when we dot two vectors which have integer entries, the result itself is an integer. So if we were to take every single element in S50 and dot it with v, we'd get a list, and that list would consist of different numbers, all of which are whole numbers, all of which are integers. And so we can actually say something then. We can say that there must exist u in S50 such that when I dot v with u, I get some number which has absolute value bigger than a half S50. Why is this true? Well, let's just suppose that S50 had size 1000 for argument's sake. So let's suppose S50 had size 1000, and we know that when we take each of those 1000 elements in S50 and dot them with v, we're going to get a different whole number. So what's kind of the worst case scenario is maybe if we start with minus 499 with one of the integers, minus 498, minus 497, and so on. So we're writing this list of integers, and we know it's got to be 1000 different integers. So then it would go up to 499, but it would have to include 500 as well. And that would give us 1000 integers. And in fact, because we know 0 is not on this list, because if 0 was on this list, we'd have a contradiction straight away. Or, sorry, we'd have proved the statement straight away. So if we had 0 on this list, that would contradict the property of v. So in fact, we could probably say 501 here, or if we wanted to put minus 500 here. Doesn't matter too much. But the key thing is we're going to get one of these numbers has absolute value at least half of 1000. So in this case, 500. And so this is kind of the pigeonhole principle in action. So in other words, we have that there is some vector u in S50 such that the v dotted with u is going to have size at least, or is going to have magnitude at least half of the size of S50. Now, we're going to use this to help us prove the result. Okay, so we have that there's some vector u in S50 such that v dotted with u is at least a half times the size of S50. Now, what can we do with this? Well, let's start with 2021. We know that this is bigger than or equal to the size of v because v is a tan vector in S2021. And now by the Cauchy-Schwarz inequality, this is going to be bigger than or equal to v dotted with u divided by u. And now we know that u has size at most of 50, and therefore 1 over u is going to be bigger than or equal to 1 over 50. So this is going to be bigger than or equal to this thing here. And now v dotted with u we know is bigger than or equal to a half S50. So this is going to be bigger than or equal to 1 over 100 times the size of S50. So if I multiply both sides by 100, I get that S50 is less than or equal to 202100. So what is that? 202,100. So we've proved that S50 must be bounded by this number here, 202,100. Now what I'm going to do is show that S50 actually has to be bigger than this size here by showing that there's a subset of S50 which is bigger than this guy here. So what is that subset? So we're going to say that subset is we're going to call T, and it's going to be the set of x, y, z for which x, y, z is tanned. So it's a non-zero vector with integer entries, and each of x, y, and z are less than or equal to 29 in absolute value. But also we can't have each of x, y, and z having absolute value 29. So we'll say that x plus y plus z has to be less than or equal to 86. So this ensures that they can't all be 29. And that's slightly important in just a second. We'll see why that's important in just a second, sorry. So firstly, we notice that, well, what's the biggest size a vector could be in T? So let W be in T. Then what's the absolute value or the size of W? Well, it's going to be at most the square root of 29 squared plus 29 squared plus 28 squared. Now, we want to show that this number here is actually less than 50, and there's a few ways you can do this. You can just plug it into your calculator, but let's imagine we don't have a calculator for this. So how can we show that this is less than 50? Well, let's think about multiples of 25. So I'm going to write 29 as 25 plus 4. So this is going to be 2 times 25 plus 4 squared plus 25 plus 3 squared, like so. And now if I just expand this like I would normally, this is going to be 2 times 25 squared plus 16 times 25 plus 4 times 4 is 16 times the 2 here is plus 32 plus 25 squared plus 25 times 3 times 2, which is 150, so 6 times 25 plus 9, all square rooted like so. And now let's bring everything together. So I've got 2 times 25 squared plus a 25 squared there, that's 3 times 25 squared, plus 16 times 25 plus 6 times 25 is plus 22 times 25, plus 32 plus 9 is plus 41, like so. And now let's group up to let's bring everything in terms of 25. So this is going to be 75 times 25 plus 22 times 25. Well, I'm going to write it as 23 times 25, and then this 41 here will just become a 16. And so what is this number here? 75 plus 23, or I can actually just say that this 16 here is less than 25. So this all becomes less than square root of 99 times square root of 25. This is less than 10, this is 5, so this is going to be less than 50. So all in all, we've shown that if we take an arbitrary vector W in the set T, then W has to have size less than 50. And what does this tell us about T? That means that T must be a subset of S50, because every vector in T is tanned, and its size is always at most 50. So T is less than S50, or so it's a subset of S50, so that means that the size of T must be less than the size of S50. And we're going to use this to prove that S50 has to be actually bigger than this number here, which will mean we get our contradiction. Okay, so we have that T is a subset of S50. Now, what is the size of T? Well, we know that the size of T is certainly going to be less than the size of S50, so we can say that S50 has size bigger than or equal to the size of T. And what is the size of T? Well, we know if we look at the definition of T, it contains all tanned vectors, so that's vectors with integer entries, and each of the integers have to have magnitude at most 29, and x plus y plus z is not allowed to be 86. So if we imagine we just consider a slightly bigger set, so this is a set of all vectors with integer entries where x, y, and z have absolute value at most 29, well then there's going to be 59 cubed options, or 59 cubed elements in that set, because, well, what are the options for x? X could take any value between minus 29 and positive 29. There's 59 values there. There's 59 values for y and 59 values for z, so 59 cubed. However, we do have to subtract a small number here. We firstly have to subtract off 1 because we're not allowed to have the 0 vector. Yeah, because it's a tan vector, we're not allowed to have the 0 vector. And we've also got to subtract off 8 because of this condition here. X plus y plus z cannot be 87. In other words, x, y, and z cannot all have magnitude 21. And the reason we have to take off 8 is because as the case is x equals plus or minus 29, y equals plus or minus 29, and z equals plus or minus 29, which gives us two cubed potential vectors which have absolute value of x, y, and z all being 29. So we do this 59 cubed minus 9, and you can just check this by working out what this number is. It's going to be 205370, but in particular it's bigger than 202100. And then we get the S50 is supposed to be less than or equal to 202100, but simultaneously bigger than 202100, and of course this is impossible, and that is our contradiction. And therefore for any tan vector we take of length at most 2021 is perpendicular to any tan vector. Is perpendicular to there exists a perpendicular vector of length at most 100, which is perpendicular to it, and that solves our problem. So I hope you have enjoyed this video. In fact, you can have a look at the numbers involved in the problem and see if you can make the bounds slightly better. So obviously there's a big discrepancy between this number and this number, so can you perhaps reduce some of the numbers in the problem to get slightly stronger bounds? But I'll leave that as an exercise to you. Anyway, I hope you have enjoyed this video. Thank you for watching. I'll catch you in the next one. Have a great day.